Hi, I'm Kathryn Neugent, and I am a PhD candidate at the University of Washington and a researcher at Lowell Observatory. And I'm going to talk to you about the binary fraction of red supergiants. So why do we care about binaries and massive stars in general? And so binaries really change a star's evolution. If you just have a single star, it's existing by itself, it's not interacting with anything, and it's losing mass through stellar winds. But if you have a binary, they might be interacting. And as you can see in this little image here, they might be experiencing Roche-lobe overflow. And so one of the stars might be sucking material off the other, and this would very heavily influence how a binary star would evolve throughout time. And so understanding the percentage of massive stars in binary systems is really important to understanding massive star evolution in general. And more importantly, a lot of massive stars are in binary systems, and so depending on the distance between the two stars, short period or long period systems, the percentage is anywhere from 30 to possibly up to 100% of main sequence hydrogen burning OB stars in massive binary systems. And so when I started this research a couple years ago as part of my PhD thesis, not very many red supergiant binaries were known. The number was around a dozen. And a lot of this is because if you take a light curve of a red supergiant and you try and find whether if it's in a binary system or not, this is quite hard because they themselves, even as single stars, are incredibly variable. And so they have these huge convective cells that you see in this simulation by Chiavasa that change on the order of days, months, years, decades. And also they have these eruptive mass loss events that make getting a light curve difficult in determining whether they're in a binary system from their light curve or not. And so because of this, not very many, as I said, around a dozen were known. And so the first question I asked myself was what type of star would be in a binary system with a red supergiant? Would you see red supergiant with, M dwarfs or not? And so red supergiants come from 8 to 29 solar mass initial mass stars. And so stars less than this aren't massive enough to become red supergiants. Stars more massive than this generally go from an O star into a Wolf-Rayet star phase. And so the question was, if you take the least massive star that turns into a red supergiant, how long does it live before it turns into a red supergiant? And so a B star, an 8 solar mass B star, will turn off the main sequence and become very quickly pass through the yellow supergiant phase and then become a red supergiant after around 7.5 million years. And so if you look at a 3 solar mass star, it's going to take a 3 solar mass star around 7.5 million years to actually enter the main sequence. So before that, it is a protostar. So any star less than 3 solar masses will not be formed by the time an 8 solar mass star has reached the red supergiant phase. And so this tells us, or if we first compare a 3 solar mass star is about an A0 dwarf. And so any star more massive than this could be the companion to a red supergiant. Any star less massive than this will still be a protostar by the time a red supergiant has formed. So stars more massive than this are generally B-type stars. And so this tells us that red supergiant companions will primarily be B-type stars. There might be some O stars in there, but due to their very, very short lifetimes and just the initial mass function telling us that less of them are produced, generally B stars would be the companions. And if we look at the known Milky Way systems, here are 5 of the dozen known. All of the companions are B-type stars, and this is true for all of the dozen. They all have B-star companions. And so the first question is, how would we find them? And so here we have the spectrum of a red supergiant, and it's characteristically kind of strong titanium oxide bands that tell you that this is a red supergiant spectrum. And so if we take the spectrum of a star, we're looking for this, and we're also looking for the indication of a B-type star. And so here we have the upper Balmer lines indicative of a B star. And now, while it would be great to have spectroscopy of everything in the sky, generally we have more photometry. It's easier to obtain, and there's also a lot of archival photometry. And so I first wanted to try and photometrically identify red supergiant B star binaries. And basically the premise is a red star is going to have more flux in the red. A blue star, like a B star, will have more flux in the blue. And if you put them together into a red supergiant B star binary, you get this black line that's the combined spectrum. It has about equal flux. And so photometrically, one of these binary systems will look different than just a red supergiant or a B star by itself. And this can be shown in this color plot. We have the black are some model simulations I ran combining Mark's red supergiant models with B*06 B star models. And so we have U minus B on the x-axis and R minus I on the Y. And we have the local group galaxy photometrically confirmed stars, or spectroscopically confirmed stars, that are red supergiants in magenta and B stars in cyan. And so you can see that kind of this little region in the red triangle is what I'm interested in. I believe these could be red supergiant B star binary systems. And so using archival photometry, I then went out to try and spectroscopically confirm a sample of red supergiant B star binaries in local group galaxies of the small and large Magellanic Clouds, as well as M31 and M33. And using the MMT in Tucson, as well as Magellan done at Las Campanas, we brought the total number of red supergiant binaries known up to 250 in just a couple of years. And so this project was very successful. And here's an example spectrum of one of them. You see the nice titanium oxide bands, redwards of 6,000 angstroms. And if we zoom in on where the upper Balmer lines are, there they are. So this is a nice red supergiant B star binary in the Large Magellanic Cloud. So next up, I wanted to determine the binary fraction. So I had a good sense of the number of binary red supergiants, but to get the fraction, I then needed to divide by all red supergiants. And so first I have focused on the Large Magellanic Cloud as kind of my first test case. And so here is a nice color magnitude diagram of near infrared colors that shows that the foreground stars have been removed using Gaia. And so here we have two mass colors of stars in the Large Magellanic Cloud. And thanks to work by Ming Yang, we can now very nicely separate out the red supergiants from the AGB stars. And so this shows just kind of general regions of where the different types of AGB stars and the red supergiants lie in color magnitude space, and the black triangles are spectroscopically confirmed red supergiants in the Large Magellanic Cloud. And so this allowed us to obtain a complete sample of red supergiants in the Large Magellanic Cloud. And then I wanted to figure out which of these were binaries. And so we had previously observed around 200 either single or binary red supergiants. And so we could feed this information along with their colors, UBVI from Zaritsky, as well as their near infrared, their near UV flux from Galax. So we could feed all of that information into a machine learning algorithm. And so I used k-nearest neighbors to attempt to classify the remaining red supergiants into either single or binary. And so on the left plot, we have the observed and spectroscopically confirmed stars, and you can see that the red ones are single and have redder colors, whereas the binary ones have a nice blue excess, as you would expect from having a B star companion. And then on the right, we have all of the red supergiants that have been classified using the k-nearest neighbors approach, and the bluer the star or the bluer the point, then the more likely it is that it is a binary, and the redder the more likely it is a single star. So I was able to use this to determine the observed red supergiant OB star binary fraction, and got a number around 13.5%, with the errors coming from just the error in the k-nearest neighbor classification. And so we believe our completeness is down to a log luminosity of greater than 4. Below this, we do not believe that our photometry is complete. And this is the total number of red supergiants of 1,820. Now, we also wanted to take into consideration any observational biases we may have encountered. And so to do that, we used BPAS, the code created by J.J. Eldridge in Auckland, and used that to determine the percentage of binaries that might have been in eclipse when the photometry was taken, and thus we would not be sensitive to detecting them, and found that to be around 3.6%. And then also binaries with compact companions, our photometric selection was not sensitive to those and got 2.4%. And so we believe that our final binary fraction is essentially around 20% for the red supergiants in the Large Magellanic Cloud. And so going back, I initially mentioned that the unevolved O-star binary fraction was 70 to even 100%. And O-stars, many of them turn into red supergiants. And so essentially, why is this number now so much smaller? The basic answer is that red supergiants are really big. And so they're going to interact. If you have two O-stars that are close companions, they are going to interact before the more massive one turns into a red supergiant. And in many cases, they might even merge. And so only the most separated systems will form a red supergiant binary. And so this is why the 20% number is so much lower, and it actually is in accord with kind of what evolutionary models predict. And so now my next steps are focusing on determining the binary fraction as a function of metallicity. And so I'm doing this in M31, M33, and the SMC. I'm also looking at merged red supergiants in the galaxy and trying to find them by measuring their rotational velocities. Red supergiants that have merged should have higher rotational velocities than those that haven't. And then also I found a bunch of new fun red supergiant binary systems that I'm enjoying looking into. And so thank you so much. Special thanks to my advisor, Emily Levesque, as well as my collaborators, Phil Massey, Nydia Morale, and Maria Drought. Thanks.